Hello everyone, and in this video we are going to talk about something called a wave equation, right? We already know what a wave equation is, so we are going to explore that wave equation. So this is also a second order equation, as you know, and it will look like this: u dt minus uxx is equals to 0. This is called the wave equation, and more particularly speaking, this is called the one-dimensional wave equation. It's called the, so let's say this is in some domain, right? For now, let me not specify the domain. I will tell you later. So for now, let's just understand that basically this is given in some region, yes, and it's called one-dimensional. It's called one-dimensional wave equation. Okay, why is one dimensional? See, this sort of equation, what happens is this, this depends on essentially two variable, as you can see, and the variable are t and x, right? And this t, yes, this is generally speaking will be something called a time variable, right? And as you know that this is always going to be positive, so t is always non-negative, that is t greater than equal 0. Yeah, and it is a one-dimensional thing, right? Of course, time, right? And then there is this x is what? X is the space variable. So depending on the problem, this x can be one dimensional, this x can be this x can be one dimensional, or this x can be two dimensional, or any higher dimensions also. So basically, generally speaking, in higher dimension we write it like this. So this is one dimensional, and similarly we write it like this: minus, let's say, uxx plus uyy equals to 0. If you write it, this will be 2D wave equation. And we do not explicitly write it like this. What we do is we write this thing as, this is equivalent to ut minus Laplacian of u equals to 0, or we also write it like this: ut minus grad square u equals to 0. So sorry, not utt, okay, here also utt. Okay, so we write it like this, yes. And essentially what is happening is these are all same, it's just a notation thing, right? Now in higher dimension also you can use, see, in two dimensions. So basically the space variable is 2. It can have 3 dimensions, so it is will be xyz, and in this case uxx plus uyy plus uzz, that term will be there, right? So you can go on doing this thing, and that's basically your wave equation, right? So I'm not writing the higher dimensional version. Okay, so the first thing we should know about the wave equation is this. See, this equation in particular, this is a homogeneous equation. Why? Because let's say L of u is there. What is L? L of L is this utt minus uxx. This is L, right? Yeah. So let's say L of u is there, and let's say this is equals to 0. Clear? Then this equation is called the homogeneous wave equation. Yes. And if let us say that L of u equals to utt minus uxx, and this is equals to some g, right? Some function g, given g can be 1, g can be 2, it can be function of x and y, it can be just a function of x, or can be just a function of t. So some function g, right? So this is called the inhomogeneous wave equation. Clear? Now the first thing first, we just want to know what happens to the homogeneous wave equation and what are the properties of it. Yeah, because this is very important. Once we know how to handle homogeneous wave equation, we will know how to handle the inhomogeneous wave equation. I will show you how. Okay, so let's look at the first theorem. The first theorem is called the fundamental theorem of superimposition. So this theorem which I am writing, this is also valid for any linear equation, basically. Yes, any linear equation will work. So in case of harmonic equation also this theorem is valid. Yes, so this is fundamental theorem on superposition and essentially this is for a linear, this is only valid for linear equations. Clear? Linear in U, that is linear equation. Okay, so since this is a linear equation, as you can see, this equation is a linear equation, right? This linear equation. So for now I'm just looking for one dimensional wave equation only, yeah, for at least for this part. So we'll just look at what this theorem says. So this says that if you have two solutions, u1 and u2, u2. Okay, we start with two solutions. Are the solutions of the homogeneous solutions of a homogeneous means this source time is 0. Homogeneous linear PDE, right? Linear PDE. Yes. So think of your Laplacian, this wave equation, and if you remember, we talked about another equation, the heat equation. Similarly, that heat equation also it will work, but the thing is it has to be homogeneous. So this term, the source term, has to be 0, right? In some region R, yeah. So as I told you, I'm not going to specify right now where this region is. I will come to that later. So let's say there is some region R, in, I mean, whatever maybe in R2, R3, it depends on the problem. I will specify all that, but for now just some region R. Yes. Then you can, if you define U, which is C1 times U1 plus C2 times U2. Okay, so these with any C1 C2, any C1 and C2, okay, is also a solution, okay, of that PDE, in the region R. Clear? So what I can do is this. Maybe it is better for me to give you an, I mean, proof using just the wave equation. Yes, but you can do it for any equation, but I mean, just give you an idea. So explanation, or maybe observation, let's just say. So see, this equation is there, right? utt minus uxx equals to 0. Let's just call it 1, and u1 and u2 are two solutions, two solutions of 1. Okay, then you see, if you write c1 times u1 plus c2 times u2, which is your new u, and you take the derivative with respect to t on t, minus c1 times u1 plus c2 times u2, and you take the derivative with respect to x and x. If you look at it, then it will give you c1 times u1 with respect to t plus c2 times u2 with respect to t and t, minus c1 times u1 with respect to x and x, minus c2 times u2 with respect to x and x. Clear? Now see, this equation and this equation, if you put it together, this becomes c1 times u1 tt minus c1 xx, which is 0, plus c2 times this one, and this one is 0. Why? Because u1 and u2 are given to be solutions of this equation. So that is equals to 0. So you see that the linear combination. So what is this thing? So therefore u, which is defined as the linear combination c1 u1 plus c2 u2, is also a solution. Okay, for any c1 c2. So this is for any c1 c2 in R. So this is called the the principle of superposition, right? This is just a name. The principle of superposition, this is just a name. Yeah, so we'll call that. Clear? Okay, so now what we will do is, first of all, we will start by working on this problem. See, the thing is this problem, one-dimensional wave equation. Yeah, wave equation. Let us write it down, and then we will start by wave equation. Okay, we'll start by, first of all, solving the problem. Yes, using method of separating variables, and then we'll see some properties of it. Yes. Okay, so first thing first, the equation looks like this: utt minus uxx equals to 0. Yes. Okay, so where is this defined? Let us understand this thing. Yes, see, this is defined. Okay, generally in literature we write it like this. Yeah, let me write it this way: c square uxx equals to 0. So essentially, if c is 1, then utt minus uxx is equals to 0. Okay, so generally speaking, this c will be a constant for now. Okay, right. Okay, so c is in R. Yes, we'll assume this thing. Okay, t is greater than equal 0. So basically, from 0 to infinity, t can be anything. That's what we are assuming. And x is lying between 0 to infinity. Yeah, this is the starting point where we are starting. This is where we are starting, right? Now the thing is, this, see, what we'll do is this. What exactly does this do? Let's just understand it. So essentially, what it does is it models. Okay, vibrating steel. Okay, vibrating elastic strings. Okay, this is what it models. Huh? So think of it like a violin string and all. Yes. Okay, so okay, and what does u do? U is basically the deflection of the string. Okay, so essentially, you see, initially the string may be here, and after that, when you are plucking it, it will get deflected a little bit, right? And after that, when you leave it, it will start oscillating essentially. Yeah, so that deflection, that is basically captured using u. Yes. Okay, so here and u represents the unknown deflection. The unknown deflection of the string, that is deflection of the string. Clear? String. Okay, this one, right? So essentially, if you want to draw this if you want to write this properly, there should be some initial condition also, right? So we'll put those initial conditions. Yes. Okay, so first of all, let's just understand this thing. See, this is your t variable, huh? And this is your x variable. Yeah, so you can of course start x between minus infinity. Yes. Okay, but for this problem to work, what we will do is we put some conditions on x, some restrictions. Huh? Of course, this x is in R. Yes, that is there, but the restriction will look at it like this. See, what we'll do is this: at x equals to 0. Yeah, this is x equals to 0 line, this line, and x equals to some L line. Let's say capital L is some number, L, capital L, and this is 0. Huh? Okay, so this is x equals to 0, this line. Yeah, this line, and this x equals to L. There is another line, x equals to L. Let's just write it like this. Okay, so there will be two boundary conditions which will be given here. So essentially, it will be u at the point 0t. This is going to be 0. So essentially, this, right, on this line u is 0, and again on this line u which is lt, u x equals to lt, that is also going to be 0. Is this okay? So this is for all t. For all t greater than equal 0, we are just assuming that on these two lines this is going to be 0. Clear? Okay, so see, what it means is this. It means that the strings which we are talking about, this is fastened here. You understand that both the ends it is fastened. Okay, so it's not moving on those two points. Okay, so at x equals to 0 and x equals to 12, this not moving. Clear? And the thing is this: you see, the formation, so the motion of the string, how the string moves, that depends on the initial deflection. See, you are deflecting something, right? And that deflection is at time t equals to 0, right? So you see, let's just call that as f of x. That's the initial deflection, right? See, u, okay, for the initial condition is u of 0t equals to u of lt equals to 0. Yeah, so you see, at x equals to 0 and x equals to L, the string is fastened, right? It fastens on those 2 points, and we will be assuming that basically that is why it is 0. So it's not moving anything. There is no reflection on u at those points. Yeah. Now, the other thing is the initial deflection at time t equals to 0, that we are going to call it as f of x. So u at x equals to t equals to 0, right? So it is x at the point 0. This is f of x, right? So essentially, what we are saying is this: initially, see, the string is attached. both the points it is attached, right? Now you are, what you are doing is you are deflecting it. Yeah, you are plucking the string, right? So once the deflection is there, that deflection is done at the time t equals to 0. That's our assumption. Yeah, so we are doing the deflection at this time t equals to 0. Okay, and as t moves, we want to see how the deflection, how the string moves. You understand the deflection? Okay, so at t equals to 0, the initial deflection, let's say that is deflected by f of x, like sine x. I'm just giving you an example. I mean, it can be something else, but some function, f of x. So the initial deflection at time equal t equals to 0. Now the thing is this, we also need to know that what is the initial velocity at time t equals to 0, right? The deflection, how fast it is deflected. See, it's not enough to know how much it is deflected, right? I mean, how is it deflected? So basically this f of x will be some function which will actually tell you how it is deflected. Yeah, so let's say this 2 point, this is fastened using a string, right? So if you are plucking it here, there will be a different deflection. If you are plucking it here, I mean, you are plucking it here initially, yeah, at t equals to 0. So that's your, so at t equals to 0, let's say maybe it will look like this, right? But if you are plucking, you understand what I'm saying, right? It depends. So essentially at t equals to 0, we want to see that what is the function, how is it in a, I mean, what is the deflection, and we also would like to know what is the initial velocity of the deflection. Yeah, okay, so initial velocity is how, velocity with respect to what? Essentially at t equals to 0, I mean, what is the change, right? So ut at the point x0. Clear? Okay, so that is g of x. So f of x and g of x, those two initial conditions are there. Clear? L capital. Yes, I hope this is more or less clear to you. Ut is del u del t essentially. Yes, so this is the initial, this is the initial velocity, and this is the initial deflection. Initial deflection is at t equals to 0. Okay, and that's the velocity of the deflection. So those are the boundary conditions which are given to us. So in these are called, these two are called initial conditions. This is called initial conditions. Why initial conditions? Because these conditions tells us what was the state of the whole system initially, and this is the boundary condition. See, this will be called boundary condition. So at the boundary they are fastened, right? So basically there is no movement. Boundary condition. Okay, so now we want to solve this. How do you solve it? You remember, we are in a situation where we maybe is possible to use the separation of variable method. Okay, so separation of variable. Let's just see and find out what it will actually give us. Separation of variable. Okay, see, we start with this equation. U of xt, we write it like capital F of x and g of t. Okay, so that's the function which we are showing that, let's say that is your solution. So of course you see that, do you think 0 is a solution of this problem? See, 0 satisfies this, u identically 0 satisfies this, u identically 0 satisfies this, u identically 0, will it satisfy this? May not, depends, right? It will only satisfy this if u at the point 0 0 is f of 0, which is 0, right? Yeah, and then this also has to be satisfied. So generally speaking, if f and g are, I mean, it may not be satisfied, right? For an arbitrary f and g, it may not be satisfied, the 0 is a solution. Okay, okay, so in that case f and g may not be trivial. Is it okay? Right, now if that happens, therefore what can you say? You see, you can say that from this equation, utt is nothing but f g double prime, and uxx is nothing but f double prime g, exactly like the harmonic equation, right? So therefore if you put it in that equation, what do you have? We have f g double prime equals to c square f double prime of g. Clear? Now if you write it properly, like exactly what we did in that harmonic function, if you remember, we will get G double prime by G equals to C square F double prime by F. Yes, this is what we are going to get. Okay, so now what we have is this. Again, see, this thing is a function of t, and this thing is just a function of x. Yeah, so definitely if this is true, then this should be equals to some constant k. Clear? Okay. Okay, so we will get two different equations in that case. Therefore, hence we obtain, what are the equations which we obtain? We obtain that G double prime. Okay, one second, I did correctly, right? UTT equals to C square. Yes, so F double prime. Okay, so what I will do is this, I will put this thing here. It will make our life easier, that's why. Otherwise it doesn't matter. Let me put it here. Equals to C square K times G. Is it okay? So let me put it here. Yes. Huh? It doesn't matter, but the thing is, I wanted it to write it like this. Yes, and you also have F double prime minus K times F. This is going to be 0, right? Those are two equations which we have. And what is K? K is a separation constant which is still arbitrary. So you can write K is a separation constant. Separation constant means this is actually separating those two. That is why we call separation constant. Okay, is arbitrary. It means this is any arbitrary the same constant, right? Okay, so those two equations. Now what do? We have the boundary conditions, if you remember. Now the boundary conditions, let's look at it. Boundary conditions, what does it say? U at the point 0, I think 0t, right? That was given, is f of 0 g of t, right? And that is given to be 0. So of course that will imply that f of 0 is 0. Since if g of t is 0, then that will imply that the original equation, the solution, is going to be 0. But we have already assumed that it may not be 0, right? So that's one problem. Now u of lt, this is equals to f of capital L g of t, which is equals to 0. So this will imply that capital F of L is going to be 0. Clear? Again, the similar sort of thing. So this holds for all t. Clear? So this two holds for all t. Yes, greater than equal 0. Clear? Now see, the thing is this, we have, therefore we have that equation, right? F double prime minus k times f, this is equals to 0. That equation was given, and moreover f0 equals to f of L equals to 0. Those two equations are given here. We can solve this equation, if you remember. Yeah, this is like an eigenvalue problem. Yes, this is, so let's call this, I don't know what it's we were calling, maybe let's call this one 1. Doesn't matter, let's just call it 1. Okay, so solving 1, what do you get? Yeah, so you have to do this thing. Yeah, please check this part. I'm not solving this thing properly. I mean, I'm not doing it explicitly because we have already done this yeah, stum Liouville problem, right? Yeah, so I'm not doing this. I will just write down the solution of this equation. Yes, okay, so the solution in this case looks like this: fn of x equals to sine of n pi by L times x. Okay, and of course n equals to 1, 2, it goes on doing this thing. Yeah, that is your fn of x. Yes, you remember we learned how to solve sum Liouville problem. So exactly like this. Yes, so you do it for negative, positive. So this is what sort of equation? This is a regular sum Liouville problem, right? For a regular sum Liouville problem, you can solve the equation, and you can find out whether there are real eigenvalues, negative eigen, sorry. So we know that all the eigenvalues are real. So now you just have to find out whether they are negative, positive, or 0. So you can actually figure that part out, and you can show that the eigenvalues all look like this. Yeah. Okay. And what are the eigenfunctions? Such that fn's are this, and these are the eigen functions corresponding to the eigenvalue. Okay, So I mean the eigenvalue which you have, that is, what is this part, k, right? One second, this is k, yeah, k. So k will be minus n pi by l square. Yeah, that's your eigen value. Okay, so of course n is again n equals to 1 to all of this is true. Clear? Okay, now what we'll do is this, we'll put it in the other equation. This value of k and fn, we'll put it in this equation. This is f, right? So we'll put it in g. Okay, so therefore what do we have? That is, therefore putting it in g, we have g double prime plus, let us, maybe I can call this thing as lambda n. So lambda n squared g equals to 0, where lambda n, we'll call it as c times this thing n pi by l. Is it okay? So I mean, you will just multiply this thing. You see, we'll just multiply this thing. Yeah, c times kg. K is this. K is this. So we can just put it together like this. Okay. I hope this is correct. C square g square minus c square. Yeah, fine. This is fine. Yeah. Okay. Now, if we can write it like this, now what is the general solution? So general solution is given like this. General solution of this problem is gn of t. Why gn? Because for each lambda n, you have one different equations, right? So gn of t is nothing but bn times cosine lambda n t plus bn star, let's just call another constant bn star, times sine lambda n of t. Is it okay? Yes. So that's therefore the solution un of xt, for each n, un of xt is a solution, right? And that will be given like gn of t fn of t, so which is nothing but bn cosine lambda n t plus bn star sine lambda n t, and then sine of n pi by l times x. So this is for n equals to 1, 2, all these things. Is it okay? Okay. So now the thing is this, what we need to do is this, we need to find out what is the exact solution. Yes, and to find out the exact solution, we have those two other conditions also. Remember, where is it? Yeah, initial condition. These two initial conditions are there. We just used boundary condition. Now we'll put initial condition. Okay. Okay, so now since this un is the solution, what is u? U is basically the sum of the solution, superposition, right? So what is u of xt? U of xt is nothing but summation n equals to 1 to infinity un of xt. I hope this is clear. Yes, and what is this thing? This is summation n equals to 1 to infinity bn cosine lambda n of t plus bn star sine of lambda n of t, one second, yes, and then sine of n pi l by l. Okay, n pi l times x. Yes, right. Now we know that the initial condition, if you remember, u of x0, u of x0, what is it? This is equals to f of x, that is given to us. Yeah, so f of x, now if you put it in here, you see this is nothing but summation n equals to 1 to infinity t equals to 0. So this part is there, this part is there, sine of 0 is going to be 0, so that's not there. We are only left out with this. So we have bn, and then cosine 0 is 1, so you don't have this thing, and then n sine of n pi x by l. This is what we have. Now you see, we just have to find bn and we are done, right? Bn we have to find because f is given to us. So basically, if we can find bn in terms of f, we are done, right? And you know how to do that. How is it? So essentially, you use the Fourier series. Yes. So here now, this, therefore, what are bn's? Bn's are nothing but 2 by l and then 0 to l f of x sine of n pi x by l dx. Clear? So this is for n equals to 1, 2, it goes on like this. These are bn's. Yeah. Now you also remember that satisfies the initial velocity, right? Also, see, bn's we got. Now we just have to find bn star. So how do you find a bn star? You see, it is given that del u del t, right, at the point evaluated at the t equals to 0. Remember, see, this condition, where is it? What is the boundary condition? Yeah, you see, del u del t evaluated at the point t equals to 0 is g of x, right? So we'll put that condition, del u del t evaluated at t equals to 0. Huh? So that is nothing but we have to write down summation n equals to 1 to infinity. Okay, I take the derivative inside. Yes. So for now, we'll just assume that we can actually take the derivative inside. Yeah, this is not always true because we are doing infinite sum, but in this case it is actually. But now we are not going to explain to you why. So bn star lambda n, it has to something to do with uniform convergence. Okay, lambda n of t, and then sine of n pi x by l. Okay, and this is at the point t equals to 0, evaluated at t equals to 0. I hope this is clear. Okay, one second. Yeah, fine. I will just take the derivative. Yeah. So now you see, at the point t equals 0, if I put t equals 0 here, it comes out to be this. This is nothing but bn star, right? And then lambda n sine of n pi x by l. Okay, and this is nothing but g of x, that's given to us, g of x. So again, this is in your Fourier sine series, right? And you can find out what bn star lambda n's are. What is bn star lambda n's? They are nothing but 2 by l, and then 0 to l g of x. Okay, I hope this is okay. G of x, yeah, sine of n pi x by l, sine of n pi x by l. Yes. Okay, and where lambda n, you remember lambda n's are nothing but c n pi by l. That's what we were assuming. See, we assume somewhere, right? What is lambda l? Where is it? Yeah, see, lambda l. Yeah, okay. So if you put it there, you see, you get that what is bn star lambda n? This is nothing but 2 by c n pi, and then you have 0 to l g of x, and then sine n pi x by l dx. Yes. So see, g and f is given to us, right? So once this is given to us, you just put everything together, and then you get your solution, right? Okay. So let me do that. See. Okay. So what is u of xt? In this case, this sum, right? So that is nothing but summation n equals to 1 to infinity bn. Yeah, I will write bn like this only now. Yes. See, the thing is this bn star, if you look at it, this bn star, yeah. Oh, I should write it bn star. Okay, this bn star, if you think about it, okay, they actually are going to be 0. So see, what we'll do is this, for simplicity. Yeah, of course, you see, if g is given, you can put everything together and you get a solution, right? That is not a problem. But for this simplicity, what we'll do is this: we'll start by considering that the initial velocity is also identically 0. So consider that g of x is identically 0. It doesn't have to be. Is it okay? So what I will do is this. I am just doing it for simplicity. Clear? Just to make you understand what's going on. That's the only idea behind this. Yes. Otherwise, don't have to be. If it is there, you just put b star, all these coefficients, whatever the values are, you will get a solution. That's not an issue. Okay. So if you put that here, what we'll see is this. You will get u of xt. Okay, to be summation n equals to 1 to infinity, and then bn. Clear? Bn are the constants, if you remember, the cosine lambda n t and sine of n pi x by l. Yes, and this is lambda n is c n pi by l. If you remember, that's u lambda. Now um, see, we can actually sum this series. Yes, I mean, what I am trying to say is this: we can have an explicit form of it, a finite form. Yes, see, cosine cn pi by l times t, yeah, times sine of n pi x, n pi by l x. Clear? So this is nothing but half, note, note, nothing but half, and then you can write it like this, right? Sine of, I think it is, yeah, n pi by l x, right? N pi x by l minus ct, minus ct. Okay, and plus sine of uh, n pi by l x plus ct. Clear? So that's what we are getting. Okay, this is just a way of writing it, nothing special is going on here. So this is what, now this is clear, right? Yeah. Okay, so therefore if you put that part here, what do you get? U of xt will get it like this, half times, yes, summation n equals to 1 to infinity, then you have bn sine of n pi by l, n pi by l x minus ct, x minus ct, plus half times summation n equals to 1 to n infinity bn sine of n pi by l x plus ct. Okay, one second. Okay, fine. This is not required. Okay, right. Now you see these two equations. So I mean, what we can do is this. So essentially, these are like x minus ct and x plus ct, right? I mean the variables. So what we'll do is this: we can just write it like this. Therefore, u of xt can be written like this. It is half times f star of x minus ct plus f star of x plus ct. If you look at it as a function of x minus ct and x plus ct, this we can just write it like this, right? So this is just a way of writing this thing. Yeah? So okay, this is just a way of writing it, simplified, simplified. Yeah. So where f star uh, is the odd periodic, is the odd periodic extension of f, extension of f, okay, uh, with period 2l, period 2l. Yes, so this is your f star. You remember this is exactly the same sort of thing which we did in Fourier series. That is what we are exploiting here. Yes, so f star is basically the odd periodic extension, and we are using that f star to write this solution in a much simplified way. That's the idea. Clear? Okay, what I will do now is we'll just look at one very simple problem, and then we'll go from there, right? Right. So let's look at one second. Yes. Okay. Fine. Let's look at this problem. A similar problem. Yes. Wave equation utt minus uxx equals to 0. Yeah. And the initial condition which is given to us is f of x. Yeah. F of x. So of course those 0 on the the okay boundary conditions are 0, are 0. So essentially the same thing which we did there. G will also assume it to be 0. Okay, so G is assumed to be 0. The only thing is f will just put some condition on f. Is it okay? So let's say if I'm putting the condition is 2k by l times x. Yeah, if 0 less than x less than l by 2 and 2k by l minus x if l by 2 less than x less than l. Is it okay? We want to find out what is the solution in this case. See, if you have something like this, if g is identically equals to 0, b n star, this is 0, right? See, G is identical 0, Bn star is going to be 0, Bn star is 0. Yeah, so u will look like this. You see, u will look like this. Okay, now if you put all of this together, okay, what we'll do is this. I will just write down the answer. I just want you to check this part. Check. So if you put everything together, what you get is u of xt will look like a series. It is 8k by pi square in this case, and then it is 1 by 1 square sine of pi by L times x cosine pi c by L times t minus 1 by 3 square. It's a very nice form, right? Sine of 3 pi by L times x, and then cosine times 3 pi c by L, okay, times t, and then it will go on doing this thing. Yes, so this is basically your solution in this case. Here it's an infinite series, of course, but you see here also the solution we got as an infinite series, and this is a simplified version, of course, but here we're just writing that series here, and that is going to be your solution. How do you find it? You don't have to do anything. You just put this in this, you see, u will look like this, right? Yeah, you just have to find out what are the eigenvalues and the eigenfunctions, and then you put that the value of this thing, you see. Yeah, so you have to find what bn's are. Bn's are essentially 2 by L. If we already know, and then you multiply it by sine. Use the fact that sine is a odd function, so sine times sine, the product of two odd function, that is going to be an even function, and then sine with cosine, that is going to be an odd function, huh? So use those facts and then integrate it. It makes your life much easier. Okay, okay, fine. Right, so with this, what I will do is I will going to end this lecture here, and then in the late lecture we are going to study more about wave equation. Thank you.